Okay. Thank you, and thanks to the organizers. Today I'm going to discuss about our recent work, which lies somehow at the intersection of entanglement theory and computational complexity. So I guess this morning it looks like we are back to the basics, and I will also go back to the basics with pure state entanglement theory. So almost everything, we can say that almost everything is known in this theory. Actually, the previous talk probably demystifies this statement, but so pure state entanglement theory. I have to convince you that if we somehow change our perspective, we can still get new insights in this theory, and I have to convince you in this talk that this is the case. So in this setting, we have two parties, Alice and Bob, which are distantly separated, and they share some entanglement in the form of pure states, and we can imagine that they have some IID copies of these states. And given the spatial separation, they can only perform some restricted class of operations, which are local operations on the subsystems and classical communication. And in particular, we know that the most useful form of entanglement is in the form of these entangled bits, or E-bits, which can be useful for tasks like quantum teleportation, super dense coding, or quantum cryptographic applications. And therefore, it makes sense to ask if the two parties share some arbitrary pure state, and I wish to convert this state into this purified form of entanglement, we may ask what is the optimal way they can do it, and this is the task of entanglement distillation, but we can also ask the converse task, which means if they start from these E-bits, what is the minimum amount of these E-bits that they need to consume to synthesize some target state. And in particular, the question is, what are the optimal rates? And this is very well established. So in the asymptotic case, we know that the von Neumann entropy captures both asymptotic rates, so both the distillable entanglement and the cost. In the infinite many copies setting are captured by this quantity, while if we go into the single-shot regime, for the distillable entanglement, the smoothed mean entropy captures the optimal rate, while the optimal rate for the entanglement cost is captured by this smoothed max entropy. And here I'm not going, it's not needed for me to define these quantities, I'm just saying that this is very well established. However, this picture misses, I think, a fundamental constraint and a fundamental observation, which is that somehow the two parties have some limits which are given by their physical situation, and in this case, these limits are turned into the fact that they can only apply these LOCC operations. But it makes sense if we look at a physical constraint that they can only apply actually also computationally efficient operations. And in this work, what we do is exactly this. So we consider this setting where the two parties can only consider are computationally bounded, we say, and they can only apply circuits that turn in polytime in the number of qubits, so where the number of qubits is the local size of the input state, and they can also act on at most poly many copies of the input. And then the immediate question is, what are the resulting computational entanglement measures, namely the computational entanglement cost and the computational distillable entanglement, which means that we want to ask what are the optimal rates when the two agents are computationally bounded. And this work essentially tries to capture this question, and let me stress that if we only limit ourselves to poly many samples, to sample-efficient algorithms, we still are able to get the von Neumann entropy rate. So limiting ourselves to sample complexity, to efficient sample complexity, doesn't really change the picture. In the previous introduction, however, I missed some fundamental observation, which is that if we look at the optimal protocol, this, of course, depends on the state. So somehow we need to talk about these two agents having perfect knowledge about state. However, this somehow contradicts our framework because, in general, it's not possible to have a perfect classical knowledge in an efficient way of the state that we want to manipulate. And therefore, it makes sense to consider two different scenarios. So we have we say the state agnostic case in which the two parties have access to some unknown input state, and they have access to poly many copies of this unknown input state, and for example, they want to distill entanglement from it. or we are in the state-aware setting, which the two parties actually have an efficient classical description of the state. And in this case, by classical description, I mean that they have access to the global circuit that prepares the state. And we call this setting state-aware or a public key scenario. And now let me just summarize the result that I'm going to discuss. So we will prove some achievability statements and some no-go statements. So the achievability statements will essentially means that we will need to come up with some computational efficient protocol that achieves some given rates. And on the converse, we will also establish optimality bounds, which means that we will prove that in a worst case setting, so for some class of states, these rates will be actually optimal. And in particular, we show that for the distillable entanglement, essentially the mean entropy of the state and not anymore the von Neumann entropy captures the optimal distillable, computational distillable entanglement, while for the entanglement cost, the optimal cost will be maximal. And let me stress that these results essentially are independent of the value of the actual von Neumann entropy. So even if the von Neumann entropy of the state is a constant, in the worst case, the entanglement cost can still be maximal. And even if the von Neumann entropy is maximal and the mean entropy is constant, still the distillable entanglement will be very small. And to go back to what I introduced before, so this optimality statement goes into this existence scenario, which means that we prove that there is no better computationally efficient protocol that achieves this given rate. But we also have this state agnostic scenario and the state aware scenario. And interesting, we prove that for these two settings, which seem apparently different, we get the same optimality bounds. And in the state agnostic scenario, we get the same bound by considering only sample efficient protocols. So they don't need to be computationally efficient. While in the state aware setting, we assume computational efficiency, but the state now are efficiently preparable. And let me stress also that in this second setting, we need to make computational assumptions that I will discuss later. So to show you how the proof of the result works, I need to introduce this concept of pseudoentanglement. So we said that two families of states are pseudoentangled when they display a gap in their von Neumann entropy, but they are still indistinguishable to computationally bounded observers. And this means that in particular we can consider two different scenarios. We have the public key computational undistinguishability and the statistical undistinguishability. And this somehow mirrors the two settings that I introduced before. So in the public key scenario, the computationally bounded observer has access to some key which contains the classical description of the state. If the two families are public key pseudoentangled, then it cannot distinguish between them with computationally efficient algorithms, even when it has access to this public key. On the converse, in the statistical undistinguishability case, there is no classical description, but the agent is only sample efficient and not computationally efficient, and still cannot distinguish between the two families. And in this second case, we don't require actually efficient state preparation. And how can we show, for example, the no-go results on the state agnostic scenario? Well, we need to come up with two families of states which are statistically pseudoentangled with an approved gap in the von Neumann entropy. And if we want to prove the log K upper bound that I showed you before, we essentially need to come up with the following set of families. So the first is very simple. We just pick R random states, while for the second we pick this ensemble that we name R subsystem states, which are essentially formed by a small R subsystem on superlog qubits, followed by some classical permutation on U pi. And we can prove that these two ensembles are statistically indistinguishable, in the sense that any agnostic distinguisher having access to many copies of the states cannot distinguish between the two families. And now it's very simple to show, using this construction, how we can get the log K bound. So first we assume by contradiction that there exists some state agnostic and sample efficient protocol that achieves some given rate R. And in particular, if this rate R exceeds the entanglement content in the low entanglement ensemble, since the extractable rate in the low entanglement ensemble is information theoretically bounded by the von Neumann entropy, this means that in the EI ensemble, we will be able to distill more than in the E-low ensemble. And therefore, there will be a gap in the distillable entanglement, and we will be able to tear apart the two classes of states, and this will provide a contradiction, because the two classes of states are statistically indistinguishable. And this provides the log K upper bound on the state agnostic scenario. What about the mean entropy upper bound? So here the insight is that, so we need to change our construction, and the insight is that the von Neumann entropy essentially captures, is very sensible to details of the spectra of the state, and therefore we can build these two classes of states where essentially we have a bulk of probability distribution, which essentially tunes the mean entropy of the state, and then we have some tails which are either given by R random states or R subsystem states. And by tuning the parameter in the state, we can essentially build two classes of states where the E-low ensemble has von Neumann entropy exactly equal to the mean entropy, while the EI ensemble has von Neumann entropy equal to the mean entropy plus some term that we can essentially tune. And now this gap essentially allows us to prove the mean entropy bound by, again, a similar reasoning as before. So this proves the state agnostic scenario. Let me stress that this doesn't prove any bound on the actual computational distillable entanglement, because, of course, the optimal protocol will not be state agnostic in general. And now the question is, can we actually achieve this bound with some state agnostic protocol? And the answer is yes, and actually we can also achieve it with a computationally efficient protocol. So this protocol was originally introduced by Matsumoto and Hayashi. It was analyzed in the infinitely many copies regime, where it actually distills the von Neumann entropy rate. So it's information theoretically optimal when we have essentially exponentially many copies of the state. How does it work? Where we essentially exploit Schur-based duality, and we use this block decomposition into the reps of the unitary and of the symmetric group of the CD tensor K. And these lambda essentially are the integer partitions of K elements. And essentially one can show that if we consider this tensor product of psi AB, we can decompose this state into the local E-reps of A and B. And the lambdas essentially now are the same for both Alice and Bob. And essentially they can project onto these lambdas locally, and then they can discard the left part of the state, and they are left with this right part, and they can essentially, by inverting these unitaries, they can recover maximum entangled states at some rate, which depends on the dimension of the rep of the symmetric group. And this happens with some probability P of lambda, and it was shown that this procedure is computationally efficient when the number of copies is polynomial. So this procedure is computationally efficient, and what is left to show is what is actually the probability of distilling a given rate of entanglement, and we actually show that you can match the previous upper bound. So the previous upper bound that I showed you is actually optimal for state agnostic protocols. So these are the probabilities, and this essentially features this chi, which is the characters of the symmetric group, and then we have these traces over the representation of the permutations. And it's very easy to prove that we can get that bound. Essentially, we can bound all these trace terms by the operator norm, where this modulus of pi is the number of cycles in the permutation. And by doing this, we can essentially bound all the probabilities via this Planck-Scherel distribution of the symmetric group, and this exponential factor, which features the number of copies and essentially the mean entropy of the state. And now, if you assume that the mean entropy is largely equal to log K, we can bound the probability of failure. So the probability that we distill, for example, less than log K, and we can show that this probability actually always goes to 0 if we put some small enough constant in front of the log K rate. And this follows because even if we sum all possible lambdas, essentially these are at most the number of integer partitions, and we can always suppress this term if we choose K is sufficiently large. Now, of course, we have to remember that K must be poly n, And therefore, we can distinguish now two different cases. So either the mean entropy is at most log n, which means that to satisfy the inequality S mean larger or equal than log k, we can push log k up to S mean, and we can distill the mean entropy. On the, instead, if the mean entropy is super log, we can essentially push log k to be arbitrarily large, and we can then distill log k. So this proves that this bound is achievable by a computationally efficient and state agnostic protocol. And let me stress again that this doesn't prove any, the previous result doesn't prove any upper bound on this computational distillable entanglement. So the question is now, does there exist some computationally efficient protocol that actually gets a better rate than this? Of course, this protocol will not be computationally efficient, will not be state agnostic. And the question is actually, the answer is actually no. So there's, we can prove that this bound this optimal bound is optimal even if the protocol is arbitrary and computationally efficient. And how does this work is based on, the proof is based on a concentration bound. So we look again the two ensembles of before. So we have the EI and the ELO ensemble, which remember are essentially formed by tilted R random states or tilted R subsystem states. And if we look at the I entanglement ensemble, we can essentially use Levy's lemma to prove that for any performance measure of the protocol lambda, of the LOCC protocol lambda, we have double exponential concentration around the average of this protocol. And now we use the fact that if the protocol is computationally efficient, we have at most exponentially many different protocols. And therefore, since we have the double exponential concentration by a simple union bound, we get that for most states in this ensemble EI, essentially the result of applying the LOCC is close to the average over the ensemble. And now we use the previous fact that I showed before, that the ELO and the EI ensemble are statistically indistinguishable. And so if we start with some state, let me call it psi star, which satisfies this concentration, this will concentrate around the EI average, but by statistical indistinguishability, this will concentrate also around the ELO average. And propounding this with the maximum, we get that any fidelity that we get in the I entanglement ensemble must be bounded by a corresponding one in the low entanglement ensemble. And therefore, this means that we are somehow limited. So if the LOCC is computationally efficient, this imposes a limit on how well the protocol may perform. And this allows us to get, again, the same upper bound, but now this essentially provides a tight equality for some class of states. And now we're only left with the state-aware setting and the entanglement cost. So in the state-aware setting, essentially, we need to come up with two families which are computationally efficient to prepare, and such that Alice and Bob have a perfect knowledge of these two families in terms of the circuit that prepares the state. And now, for the first time, we need to put into the picture computational hardness assumptions. And in particular, we will use this learning with errors or LWE hardness assumption, which is widely adopted in post-quantum cryptography, which essentially assumes the following. So if we are given samples from these two classical distributions, so we either have essentially a random matrix and a random vector sampled uniformly, or we have this random matrix and we have some noisy scalar product, where this noise comes from some Gaussian, some discrete Gaussian distribution. And this LW assumption essentially assumes that under some range of these parameters, distinguishing between these two hypotheses is computationally hard, even for a quantum computer. And it was shown by Buland and collaborators that we can essentially map these two instances into these phase states in a way that the first instance will correspond to high entanglement, while the second instance will correspond to low entanglement. And the key of the state essentially is given by the output of this LWE problem. And therefore, this essentially is the construction of the public key family. So we have an efficient construction, and if we know the key, we can prepare the state efficiently. And this, by a similar construction as before, essentially allows us to prove, again, an Hugo result with the same optimal bound. And now, what about the entanglement cost? So I will not go through the proof of the entanglement cost. It's actually, the techniques are very similar, but the outcome is very different. So what happens is that in this case, in the worst case setting, the two parties essentially will not be able to dilute the state unless they consume the maximum amount of entanglement, which means that the quantum teleportation protocol is essentially optimal in this setting. And I stress that this is optimal only in terms of the entanglement consumed and not in terms of the classical communication. So of course, this must be efficient, but we are not counting the classical communication. We're not optimizing with the classical communication. And in particular, a corollary of our results is that in the pure state setting, when we impose computational limitations, essentially we have this phenomenon of computational bound entanglement, which appears in this pure state setting, which means that we have families of states for which the computational entanglement cost is maximal, while the computational distillable entanglement is near zero. And this, of course, is a phenomenon that in the pure state setting, in the information derived setting, doesn't happen. It happens only in the mixed state entanglement theory. And now let me just go through some other applications of our results. So in particular, for the task of entanglement estimation, so let's say that we want to estimate the von Neumann entropy of some mixed states. We proved that as a corollary of our results that estimating this quantity essentially requires exponential sample complexity, even when the von Neumann entropy is a constant. And this, before, was only shown for some specific values of the von Neumann entropy, usually when this was close to maximal. Also, we can get some lower bounds in sample complexity for entanglement testing. So if you want to test whether the von Neumann entropy is larger than a constant or smaller than some other constant, we get this sample complexity lower bound. And curiously, this lower bound essentially almost generalizes a known lower bound that was shown by Valiant in the classical case, so for the classical Shannon entropy. And finally, we also have applications for LOCC pure state tomography. So let's say that we have some global protocol, and we want to translate this global protocol into a local one. Essentially, an application of the Schur distillation protocol followed by quantum teleportation allows us to convert any global protocol into a local protocol just by a small computational overhead. And this is done by first distilling entanglement from the state, and then using bell pairs to teleport the state, and then essentially perform an arbitrary global protocol on Alice or on Bob. And also our results have implications on efficient state compression, because essentially all the no-go results on entanglement dilution can be used for efficient state compression, since state compression is essentially a protocol for diluting entanglement, by first compressing the state and then teleporting it. So to conclude, we have shown optimal bounds for this computationally limited scenario by showing achievability statements and worst case optimality results. And importantly, the mean entropy essentially replaces the role of the von Neumann entropy for what concerns entanglement distillation, while for the entanglement cost, essentially in a worst case setting, the optimal rate is maximal. And this result holds independently of the setting. So either we are in the state aware scenario, in the state agnostic scenario, or we prove a non-existence result. Essentially, we get the same worst case bound. And let me stress that all these results are robust to noise. So even if we allow some noise in the output, so let's say that the distillation protocol fails with some, say succeeds with some constant probability, smaller than 1, or the output state is only close in trace distance to some maximally entangled state, our no-go results still hold. And as special direction, I think it would be interesting to show if it's possible to get some achievability statement for mixed states with an computationally efficient protocol, which hopefully is also state agnostic. And in general, I would say it would be nice to explore if it's possible to generalize this result to other quantum resource theories like non-Gaussianity or quantum magic. I'm done, and thank you for your attention.
So we have time for questions. So we have questions here. No questions. Everybody waiting for the coffee. So do you have any ideas about this robustness to noise? Is that, say, a huge new open field where lots of, say, interesting open problems appear? You consider mixed states.
Yeah. Yeah, I would say like our protocol, was already like proposed by Matsumoto and Yashi, but that protocol seems to work only for pure states, and it's not clear how you can generalize this to mixed states. Before this, because we exploit crucially this fact that the E-reps are the same on both sides. While if the state is mixed, you will need to do some error correction, let's say, to get the same E-rep on both sides. Also the representation will not hold. The state representation will not hold for from mixed states. So that's I think it's an interesting question. But yeah, we still we have results for of course if the state is almost pure IID. This protocol is robust to that, so you can apply this protocol, but we still don't have results for mixed states. Yeah.
Thanks. I guess your results are also directly applicable to this, this resource theory of purity. So you have a noisy state, you have many copies of it, and you can only apply unitaries to it, and so your goal is to get like close to pure states. And then in your framework, you would then want that this unitary that you apply is like Pauli and implementable. So have you thought about that? Or
Actually, yeah, I didn't think about it, but it looks very interesting. Yeah, yeah. I wonder if maybe this Schur-based protocol could help in that. It looks like could be a way to extract purity, but yeah, I will look into that. Thank you for the suggestion.
More questions? Okay. Well, no more questions then. Coffee, I guess it is. Yeah. Let's thank the speaker again and all other speakers.